Beach Hotel, a beautiful resort in the beach. Now, Clovis Gonzaga.
I will talk about complexity-based methods for convex optimization. Complexity appeared mainly in computer science, maybe 50 years ago, when people saw that there are problems that can never be solved because they are too difficult computationally. The study of complexity for continuous optimization was done mostly by Russians, and well, it might be better to speak in Russian, because all these authors are Russian. Well, to study complexity, a study of complexity is based on these three items. The first is, let me see, a class of problems. So we want to study the computational complexity of a class of problems, and there's an oracle, and there's a stopping criterion. Let's see. A class of problems is, for instance, convex feasibility problems. We shall talk a little bit about this. Linear programming problems, quadratic function minimization, differentiable convex optimization, and, well, all problems in mathematics. When we deal with a class of problems, we must do algorithms that use some information about the problem. So the oracle is an entity to whom we ask a question about the problem at this instant. They give answers like function values, first derivatives, or cutting planes. This will appear immediately. And then there's a stopping criterion. The stopping criterion may be proximity to an optimal solution, function value, deviation in function value, or norm of gradient. And once we have a class of problems, there's a model of algorithms for this scheme. And the model is like this. This is an information set, which is empty in the beginning. At each iteration, the algorithm asks the oracle the information that he has about the problem at this point, at the point xk. Then we update the information set, by getting the information we just got and adding it to the set we had before. And then we apply the rules of the method to find the next iterate. If the next point, the point xk plus 1, is in the target, it means satisfies the stopping condition, we stop and that's it. So this is the general model for algorithms. And the performance of the algorithm is given by the number of oracle calls for solving a problem in the worst case. What's worst case? Means that any problem can be solved in this number of iterations. The complexity now is more difficult. The complexity is the performance of the best possible algorithm for this scheme. For most problems, we don't know what is the best, so we very often don't know what is the complexity of the problem. We know the performance of algorithms. And the numerical performance is the number of arithmetic operations done for solving a problem. Let's go to the first example. So what I'm doing today is I'll give some examples, some classical examples of complexity theory, and then in the final part, I will give a completely new result on a hopefully important. Most general problem method for solving a problem. We start with a big set, and we have a small target set. If you call these the desirable points, the problem is find a desirable point. So we start with a large set and a small set, and this is the class of problems. Find a desirable point. The oracle will be the following. given a point like that in there, we are able to find a cutting plane. That means a hyperplane that leaves the target set on one side, on one of its sides. So we must be able to compute, well, this is a linear inequality. And this is the oracle, a cutting plane. The method now is like this. The method finds the center of gravity of the large set, compute the center of gravity of the large set. If the center of gravity is in the target, stop, you won. Otherwise, call the oracle, compute a cutting plane, and divide the set in two pieces. Okay, when we divide a convex set in two pieces through the center of gravity, the volume of the set is divided by 2. Not really by 2, it's very nearly near 2, it's 0.64. So if we divide the set by 2 at each iteration, in logarithm of 1 over epsilon iterations, the volume, well, there's an n here because it's the radius of this. So the volume of the large set will be smaller than the smaller set, so the algorithm has to stop before this. So the method stops in 2.25 n logarithm of 1 over epsilon at most. So this is the complexity of the problem. I mean, this is the performance of this algorithm. Here's one more iteration. Yeah. So this is the performance, and
this assumes that you can find the center of gravity very fast.
Yes, that's the problem. That's the big problem. So the method of center of gravity is the best possible. It's impossible to do better than that. The number of iterations is this. This is the best possible, but it's generally not realizable because computing the center of gravity is very difficult. It may be used for dimensions like 2 or 3 or 4, but otherwise it cannot be used. So we must use simpler shapes. What are simple shapes in the world? Simple shapes in the world are balls. Balls or well-known ellipsoids. A well-known ellipsoid is a ball because we can always change the variables in the car. So let's use ellipsoids now. Let's go directly to the figures. We start with the large set being a ball. And then we call the oracle, find the center of the ball, which is easy, and divide the ball in two parts. Now the target set is there, and we divide the ball in two parts. Now come the Russians. And the Russians say it's easy to find the smallest volume ellipsoid that contains the half ball. And this ellipsoid has a volume that's smaller than the original ball. And that's the method. Each iteration, let's go to a complete iteration. Having a half ellipsoid, we had a half ball, now we have a half ellipsoid. Having a half ellipsoid, we find the smallest volume ellipsoid that contains the half ellipsoid. And then we, from this ellipsoid now, here we call the oracle. We divide this ellipsoid into two parts and find the smallest ellipsoid that contains the half ellipsoid. Okay, there's a simple formula for doing this, and each iteration can be done in n-squared numerical operations. One more iteration there, half ellipsoid, and so on. So this method, the performance now is not as good as the previous one. Instead of n log of 1 over epsilon, it will be n squared log 1 over epsilon. So this is the ellipsoid method. And now let's look at the linear programming problem. Linear programming problem is you want to minimize a linear function in a polyhedron. Polyhedron defined by ax smaller than or equal to b or x greater than or equal to 0. Or we can express it as minimize the linear cost subject to ax equals b, x greater than or equal to 0. This one can be transformed to that by adding slack variables. This one is very good for drawing, for making pictures. This is the one used by all algorithms because the difficult things, which are the inequalities, are concentrated in non-negative variables. And we call an interior feasible solution a solution that a point that satisfies this with strict inequality. Okay. Simplex method was devised by Danzig in 1948 or and what it does is it takes the polyhedron, it follows a sequence of vertices in the polyhedron with decreasing cost. These are slices of constant cost, so the cost decreases until you get to a vertex that's an optimal solution. And it was found that this is exponential in the worst case. So it's a wonderful algorithm, but from the theoretical point of view of complexity, it's bad. Then in 1978 came the Kashan-Sputnik. Kashan applied the ellipsoid to linear programming and found a solution with precision epsilon in order n squared log of 1 over epsilon iterations with the performance order n for log of 1 over epsilon iterations, like in he did more than that. He said which epsilon you should use, but we won't talk about this today. So this is this was the performance of the best existing algorithm for linear programming, but in practice it was very bad. It was absolutely impossible. Then in '84, Kamarkar wrote his interior point method with lowering from N4 to 3.5 L computations. But now the algorithm worked well. 1986, Renninger found the same complexity, but now Kamarkar had n iterations with n to the 2.5 computations per iteration. Renninger had the same complexity, but with a smaller number of iterations. I mean, square root of n iterations, but n cubed computations per iterations. Then Vaidya and me independently in '87 found this path-following algorithm with order n cube L iteration. That's the bound existing up to now. So I want to talk a little bit about how these methods work. Again, linear programming problem.
Sorry, can you remind us what are N and L?
Did I write L there? Oh, I'm sorry. I should have written log of L is logarithm of 1 over epsilon. I'm sorry.
Okay, and N is the number of x.
N is the dimension of the space.
The number of x variables.
The number of variables, yes, number of x variables. Okay. You see this L, this logarithm of 1 over epsilon will appear everywhere. So linear programming problem is this, and now if we take the cost and we try to reduce the cost by taking a step along the negative direction of the cost, we hit the boundary and there's nothing else we can do. Then comes the logarithmic barrier function. The log barrier function, remember the important thing is that the variables must be greater than or equal to 0, non-negative. The barrier function associates to each x summation of log of xi, and you see that far from the boundary, I mean when xi are large, this function is very well behaved. Near the boundary, x approaches 0, and the log barrier function goes to infinity. So it works like a barrier, and it's a very easy function because the derivatives are very simple to compute, and it's still simpler if we look at the point 1, 1, 1, 1, 1. At this point, the gradient is just minus 1, 1, 1, 1, 1, and the Hessian is the identity. If the Hessian is the identity, Newton's method or steepest descent are the same thing. They're very easy. Okay, so it's easy to do Newton method for this function. Now, we combine the objective function and the barrier function to get this penalized function. And so think of this. If alpha is very large, the barrier function, the penalty, is not very influential. If alpha is small, the barrier function dominates. If alpha is 0, then we find, and if this minimum exists, we find a point that's called the analytic center of the set. And we are interested in the points, in the minimizers of this penalized function. So we'll construct a function that associates to each alpha greater than 0 the minimizer of the barrier function, and this defines the central path. So here, polyhedron. Actually, what we have here is a problem with 5 variables in R5 with 3 equalities, with three constraints. So it becomes, we removed from there the 2-dimensional subspace and looked at the barrier function. So these are the level curves for the barrier function. And this is the central path. It's the set of minimizers of the summation of alpha times the cost plus the barrier function. It's easy to see how to draw it. If we look at a slice of constant cost here, and minimize the barrier function along this slice of constant cost, we get that point, which is the in the point of tangency of this line and the level curves. See, so this is the way of drawing the central path. Well, now, what we do with the central path? We want to follow the central path. The most important problem there is, given a parameter alpha for the central path, we want to find the minimizer of the penalized function. For solving this problem, we used Newton's direction. And this is the formula for Newton's direction. We don't have time to develop it, but this is the Newton direction, finding for centering, for a point that's on the central path. And this, well, what I say is, this is very easy to compute using a projection. So okay. And now the main theorem. The main theorem is the following. When we look at the Newton direction, if we change variables so that the variable goes to the point where we are, goes to 1, 1, 1, 1, and look at the size of the Newton direction there, this is what's called the proximity to the central point. Up to now, all was classical stuff done in the 60s. This is what's new. It was done in 1986, 87. So this is the proximity to the central point. And the great theorem, this is the most important theorem in the interior points. It says that if this measure of proximity, which is a measure of the length of the Newton step, is small. Small means smaller than 1. It's not smaller than given epsilon, there is delta, no. Smaller than 1. Then a Newton step reduces this by from delta to delta square. That's the best thing we can have in an algorithm. This is a pure quadratic convergence. So there's a very efficient way of finding a central path, a central point, if we are near a central point. Let's look at the algorithm now. Suppose, we'll not talk about initialization, that we have a point xk, we have a value of alpha, and we assume that this is near in this sense of proximity, which means, suppose that the proximity here is 0.25, 1/4. Now, we can increase the value of alpha so that in the Newton equation, the distance becomes 0.5. So this is the Newton step. The distance from this point to this point now is 0.5. We apply 1 Newton step, and the distance is reduced to the square of 0.5, which is 0.25 again. And this is the method. So the method walks along the central path, and what you get from this computation is that you find a precision of epsilon for the problem, for the solution of the problem, in order of square root of n log of 1 over epsilon iterations. And the number of operations now, you need n to the 2.5 computations, calculations to get to compute the Newton step. So this is the complexity. Okay, so this is the main thing in classical interior point methods. You follow the central path by short steps, and this is what happens in the example we had. So this is the sequence of short steps. Now, short steps give you the best performance, theoretical performance, not the best practical performance. Best practical performance is done when you take long steps. I mean, instead of just reducing a little bit, increasing a little bit the value of the parameter alpha, you do a great, large increase. And then you take several Newton steps, and you must be careful with line searches and all that. And this is the representation of large steps for following the central path. You see the central path, and we follow it by large steps. Then there was an evolution of this by doing adaptive methods. Adaptive methods are like this. You are in a point that's near one point in the central path, and you put your caret far away, which means you increase the parameter alpha by a large amount, and then you take 1 Newton step. You don't take several Newton steps as Obelix did. You take 1 Newton step and start it all over again. Then you must be careful not to get too far from the central path. And what's done is you define a neighborhood of the central path using that measure of proximity, and you move to a point in the boundary of this neighborhood, and then center by doing an iteration with a fixed value of the parameter alpha, and this goes on, and this is what works very well. The conclusion of this is, well, the winner is Jacek Gonziu. He solved a portfolio optimization problem with 1.1 billion variables and 353 million constraints. And this was done in 53 iterations of this method we just talked about in 50 minutes of a huge computer. It was the 5th computer in the world at this time. Now it's not. No. And the algorithms are more efficient in primal dual versions. I mean, there was a big evolution of this, and actually the primal dual version of what we just talked is what was used by Jacek Gonziu. Okay, this was linear programming. Now I want to go forget about constraint problems and go to the minimization of a quadratic function. Why are we interested in minimizing a quadratic function? Minimizing a quadratic function like this is the same as solving hx equals 0, which is solving a linear system. But it's more than that. The quadratic function is the simplest nonlinear function, the simplest convex function we can think about. And if you had it, and it doesn't work for quadratic functions, it won't work for anything. Then we study quadratic functions. And so let's look at the problem of minimizing a quadratic function, 1/2 of x transpose hx. This is the Hessian matrix. And suppose that the Hessian matrix is positive, definite n by n. So it has a unique minimizer. Problem is, find this minimizer. You can find it in one iteration by inverting the matrix H. But that's a big thing. That's a difficult thing. Let's see a geometrical construction for this. Constructing Krylov space methods. Krylov space is like this. We start with the point x0. We take the gradient of the function, which is hx, and look at the one-dimensional affine subspace defined by this gradient. So gradients will be gk. So we look at the space x0 plus the subspace generated by g0, which is a line. And we minimize the function along this line. And we find the first point by minimizing the function. Its minimization is extremely easy. So it's very easy. And we find a second gradient, which is orthogonal to the first one. And with this one, we can define now a space of dimension 2 by adding the new gradient. So we had the first gradient. Now we put one more gradient. And we define a second space, which is x0 plus the subspace generated by the two gradients that we had before. So look that the information set that we have is the set of past gradients. Well, this space can also be, this coincides with the space defined with the subspace of hx0, which is g0, and h squared x0, because g1 will be defined at a point that is defined, that has been defined by g1. So. And then, problem, minimize the function in the space of this subspace of dimension 2. And this gives the second point, and so on. So the general iteration is, we start with a space of dimension k minus 1, which is given by by dimension k, which is x0 plus the subspace generated by g0, g1, gk minus 1, which is the same as this, the hkx0. And then we minimize the function in this k-dimensional subspace. Question is this difficult or easy? And the answer is, it's easy. If you did your lesson up to k minus 1, extending it to one more dimension is very easy. There is a very simple formula. We won't write formula. Then, you see that these gradients, each gradient is orthogonal to the subspace of the former gradients. So they are linearly independent, and in n iterations, you find a solution. But n is not good. N may be millions or billions, so you don't want n. But it's better than this. No, I won't develop the thing, just put the result, which is the following. At iteration k, your x belongs, your point belongs to x0 plus the subspace defined by hx0, h squared, h0, and so on. So your point will be a linear combination of the components of the generators of this subspace. So it's a matrix polynomial. When you compute this function will also be a matrix polynomial. And we want the minimum possible value for this function, which is a matrix polynomial. which is given by a matrix polynomial. What do? You use Chebyshev polynomials. Now, using a Chebyshev polynomial in a clever way, you get the best possible bound for this, for f, which is defined as a matrix polynomial. And this gives you this number. And the number is, well, let's look here. The number of iterations that you need to achieve a precision of epsilon is given by square root of L, where L here is the highest eigenvalue. So the highest eigenvalue is important here. And, well, there's the norm of x0, then order of 1 over square root of epsilon. So it's not order of logarithm of 1 over epsilon, it's 1 over square root of epsilon. And this is the best possible. I mean, for the general problem of minimizing a quadratic function, it's impossible to devise an algorithm which is faster than this, with a complexity better than this. Okay, so complexity of the quadratic minimization problem, class minimization of a convex quadratic with the highest eigenvalue of the Hessian matrix smaller than or equal to L. The oracle is use derivatives, so it's a first order method, and the stopping rule is precision in function values. The complexity is, in the worst case, no problem can solve a problem of this class with performance better than square root of L order of 1 over square root of epsilon. Okay. Good. Now we go to the original part. Let's look at the quadratic problem again, the same quadratic problem, but with a little more structure. We know the condition number. So we know the condition number C, so we have eigenvalues which are all positive. We still call L the highest eigenvalue, but we know that the relationship between the highest and smallest eigenvalue is given by a number C. Okay. Method. This now, in this year, is the most important method in the world. We've done lots of second-order methods, and since problems nowadays go to millions and billions of variables, using second-order information became impossible. So if you look at a big optimization congress, now half of the papers are about first-order methods. And the most important first-order method is the method of Cauchy, which was defined by Cauchy in 1840. Actually, he invented the gradient to do this method, which is, given a point, next point will be given by zk minus a step length multiplied by the negative of the derivative, which is the steepest descent direction. So steepest descent direction, if you look at the formula now, this is the gradient of f is hz, so you get I minus lambda k h times zk. So this is the steepest descent method, and what you must do is find the step lengths that you will use. So the only thing you can do with the steepest descent method is find step lengths. So you must find a sequence of step lengths so that the value of the function is decreased by a factor of epsilon. Actually put epsilon squared because there's a square in the function. Okay. So this is the problem, and we know some results. So what's called the Cauchy step is this: you have a point. You take the gradient, get the negative of the gradient, and minimize the function along the negative gradient direction. This was studied, and there's a beautiful study using a lemma by Kantorovich, and you find out that in each iteration, you can prove that f of zk, f of z plus, the next point, is smaller than or equal to c minus 1 over c plus 1 squared f of z, where c is the condition number. Well, condition number is the relationship between the highest eigenvalue and the smallest eigenvalue. Okay, the ratio of the highest to smallest eigenvalue. Well, if you now of the Hessian. Mm-hmm.
And, sorry, locally over the entire Hessian or locally at the point that you're doing the step?
Oh, look, the function is quadratic, so the Hessian is constant.
Okay, great.
Assume that if you know the eigenvalues, you can use the eigenvalues. You don't know the eigenvalues. What you know is that you have a smallest eigenvalue, mu1, and the largest eigenvalue is c times mu1. Okay? And this is classic. This is in all textbooks. If we now accumulate this by a sequence of steps, so we elevate this to the power k to get the kth step and do some manipulation of the function, we get this. The worst case performance of the steepest descent method using the exact line search, which is the Cauchy step, is k smaller than c over 2 log of 1 over epsilon. So this is known, this is in textbooks, c over 2 log of 1 over epsilon. There's another way of doing this, which is taking short steps. Short steps is, L is the highest eigenvalue, so you take steps 1 over L, 1 over L, 1 over L, 1 over L in all iterations, and then you get a complexity which is a little worse than for the Kantorovich case, which is k smaller than c log of 1 over epsilon. Now look at this. Here you have c over 2. These bounds are sharp. It's possible to prove that the same bound holds for all known methods, of choosing the step lengths. C over 2. What we want to prove is this, square root of c over 2. And there is a proof that it's impossible to do better than this. So if you, it's impossible to find a method better than this. Again, this is Kantorovich, this is a known result, this is what we want to prove. So we want to prove the following. Assume that the condition number is given. We say that there is look here, the sequence here is 1, 1, 1, 1, 1, 1, 1. It does not depend on the point. We say that there is another sequence which is not 1, 1, 1, 1, 1, such that if you use this sequence in any problem with this condition number, what you get is a precision of epsilon in k smaller than or equal to square root of c over 2 log of 1 over epsilon. So let's look at again at the quadratic problem. We can diagonalize this problem, but we diagonalize this problem not in practice. I mean for theory, for the step lengths. We diagonalize using the orthonormal matrix of orthonormal matrix of eigenvectors, and we change variables using this matrix. And what we know is that when we diagonalize, what we get is a function now in which this Hessian matrix is the diagonal of the eigenvalues, and norms are kept between the transformed and the original problems. So if we solve this problem, we have solved the original problem. And here is the steepest descent method. X0 is given. Xk plus 1 is xk minus lambda k gradient, as we had before. And this is 1 minus lambda kq xk. Now, this matrix is diagonal, so we can say that each variable satisfies xik plus 1 is equal to 1 minus lambda k mu I xik. And after k iterations, what you have is the product of these 1 minus lambda j mu I for each variable. So you can think of each variable as separated from the others for the same sequence lambda k. And besides that, what is usually not known is that the order of the steps is irrelevant. So if you take 10 short steps, then you can change the order and you get the same thing. Because that's what it is, huh? This product. Okay. Stopping criteria. We have this function. This is the algorithm. And now, given epsilon, we have several possible stopping rules. The first one is f of x smaller than or equal to x squared f of x0, or the norm of the gradient smaller than epsilon times the initial norm of gradient, or the norm of the point smaller than or equal to epsilon. You see the epsilon square appears here because there's a square in the function. Now, we have three different stopping rules, and there is one stronger rule that implies all the other, is make all the components smaller than equal to epsilon times the initial component. So if you satisfy this, if you solve this problem, you have solved all of those. And this is what we want to do. So, besides that, since each variable is completely independent from the others, we can set the initial point xi0 equals to 1, and the stopping rule becomes xi k smaller than epsilon, because each one is, they're all independent. Then look, we had variables x1, x2, x3 to xn. Each one was associated with one eigenvalue, mu1, mu2, mu3, up to mu n. So we could have written for this first variable, instead of x1, we could have written x of mu1, then x of mu2, x of mu3, which is, we can now extend this to an infinite dimensional formulation and define the function that associates with each point in the set mu1 to 1, the value of x of mu. And now we have the process becomes the following. x0 of mu equals 1, a constant function from mu1 to 1. And for each iteration, you have this same formula. Xk plus 1 of mu equals 1 minus lambda k mu, xk of mu. And the stopping rule is all variables, all now an infinite number of variables smaller than or equal to epsilon. If a sequence lambda k solves, I put this here because it's very difficult to check this for a function that's for a function, but we'll look at this. Now, if lambda k solves this for a given mu and epsilon, then the same lambda k solves any quadratic programming problem with eigenvalues in there. I mean, instead of taking an infinite number of eigenvalues, if you take, let's say, 8 eigenvalues, they are in this infinite set, so you solve any problem. So solving the infinite dimensional problem is more difficult than solving any particular problem. Okay. So there we are. Let's look at a step. We started with a function which is equal to 1. It's not from 0 to 1 here, it's from mu1 to 1. And look at 1 minus lambda mu. So this is the function that's here, 1 minus lambda mu. Look at 1 minus lambda mu, and I chose a certain value of lambda. And for mu equals 1 over lambda, this gives 0. So this is it. This point is 1 over lambda, and this is the function, the absolute value of 1 minus lambda mu. And you see the following. I took a step. This is a large step. It's a large step because it's 1 over 0.8. Yeah, it's a step larger than 10. A large step increases the absolute value of all the variables associated with large eigenvalues. And this, so this is the picture of the function 1 minus lambda mu, a first iteration. And here I have the same picture in a logarithm scale. You see that then, that a large step increases the, let's call heavy variables, the variables associated with large eigenvalues. So a large step decreases the light variables and increases the absolute value of the large variable, of the heavy variables. Yeah, I won't go through this. Let's look in the figure. Okay. So the conclusion is this. If I take a large step, if I take a short step, all variables decrease, but they decrease very little. So a short step has a very small influence in the light variables. A large step decreases the light variables, but increases the heavy variables. So we need many short steps and a few large steps. And large steps are needed because large steps are the only way of reducing the variables associated with small eigenvalues. Well, let's do a conceptual algorithm for solving the infinite dimensional problem. It's like that. I start with x equals 1 for all the interval. At iteration k, I look for a point which with the maximum possible value of the function x. And then I set lambda equals 1 divided by this, by mu k, and take the step. Okay. Let's see this working. Here, first iteration was like this. I started with the function, this in logarithmic scale. I started with the function equal 1, and I chose arbitrarily here a point, a value of lambda, which is the inverse of the mu at this point. So, and this is the result. The function decreased here and increased there, also always in absolute value. Now, look, now I look at this function and choose the worst possible point, which is this one, and apply a step that reduces to 0 the value of function here, which is 1 over the value of mu there, and I get this. See? So I multiplied 1 minus lambda mu for the function that I had before, and now I get this. Now I look for the point of maximum, which is this one, and the function is decreased. Again, look for the point of maximum, which is now that one. And when I take this large step, look at what happens to all the other points. The value of x increases in the rest remaining points, and so on. After some iterations, I get something like this, and after many more iterations, I get this. So this is the function, x, the values of x seen as a function, and this is smaller than epsilon, and at this point I stop the algorithm. Okay? Okay, so this is it. This is what should be understood. I take an infinite dimensional problem, and I use this algorithm, which is look for the worst value of the variable, and try to reduce this one to 0. Now, I must go fast now on this. This was very nice, but it's impossible to maximize a function like this. So look at the shape of this function. No way of finding a maximum of this function. Then what I do is I discretize. So I had finite dimensional, then I went to infinite dimension, and now I discretize this thing. And this took me 6 months, this slide. The way of discretizing is this. I take the function, I define discrete points here, and I associate with each interval in discretization the constant value, which is the maximum between the maximum of the points in this interval, which is extremely easy because this function, the maximum of this function is either one side or the other. And then I use this function instead of the original continuous function. And this is what will, okay. And this is now what will happen. First iteration was this. This in blue is the actual function, and this is the discretized function. Then when I apply a second step, choosing that point as maximum, I get a new discretized function, which is above the original function. So what I have in discretized problem is a function that is above the function that I want to minimize. So if I minimize this discretized function, I've done it. So these iterations are like this. So main result is we want to solve a quadratic programming problem. What we do is we solve this infinite dimensional problem with mu1 equals 1 over c and precision epsilon. We record the sequence that was obtained for solving the infinite dimensional problem. We do it once in a lifetime. You only have to do it once, and now you apply this sequence to the original problem in any order. And the algorithm stops with this, with the desired performance. And the proof of this is here. So this is the proof of the theorem. Since you only have to do it in a lifetime, I did it. I did it for several values. Well, I did it for values c going from 1 to 1 billion. So from I don't have a formal proof of this yet. I don't know if I will find one, but I have a proof that it's correct for conditional numbers between 1 and 1 billion. This in 10 minutes of computing. Now in more time I'll have it for 1 trillion. Example, 2 minutes, yes. Example. Now I took a problem with 1 million, condition number 1 million, 100,000 variables, epsilon 10 to the minus 5, and I use 3 algorithms. First, the conjugate gradient algorithm, which is the Krylov space, and it's impossible to do better than this. There's a proof that it's impossible to go better than this, so we didn't go better than this. This is Cauchy, the Kantorovich result. Well, this is Nesterov's method, which is a great method. And in blue is what I did. We called it the magic sequence. You see it goes up and down. When we take a long step, it goes up because we increase the heavy variables. But then it goes down and see that it performs very well. This is what happens. Well, now I took the minimum of what happened before, minimum up to now, to avoid the, and this was the performance of our method, which is, it's quite good. It seems to be quite good, but this is an easy problem because I used randomly distributed eigenvalues. Now if I use, and this is what happened to the gradient, it gets, the gradient can go better than conjugate gradient. So it's very good. Now, I took very ill-distributed eigenvalues. So how do you construct a very difficult problem? Put one eigenvalue with value 1, 1 million eigenvalues with value 1 over 1 million. That's extremely ill-distributed. And then you have this. Look at conjugate gradient, goes down immediately, and all other methods take a long time, but our method goes better than all the others. Okay. Thank you.
Questions? Clovis?
Yes?
So, I have a couple questions. One of them is, how would, when you stated these results, like this is the best possible bound, and how algorithm does better than this, you stated, is this on?
It's impossible to go better than this. Okay.
Right, how would, I mean, conceptually, how could I imagine proving such a thing?
It's not so easy. Not so easy. It has been proved by Russians. And you can find it in Yuri Nesterov's book. But the way of proving that it's impossible to do something better than something is to find an example. Because it's worst case. So this is what Yuri did. He found an example. He constructed an example, which is, well, maybe this example that I just said. One large eigenvalues and a huge number of very small eigenvalues. And then you prove that it's impossible when applying any method of a class to go better than something. So this is what Nesterov did. So the proof that it's impossible to get better is always done by finding an example.
You said you don't have a formal proof in general, but you say then you have a proof up to so many billions. What does it mean?
It means that I have a sequence of lambda with the following property. If you give me a problem in which the condition number is smaller than 1 billion, and you apply this sequence to the Cauchy method, the Cauchy method with the sequence, you get 1 over epsilon. That's it. I mean, it's proved that the sequence that has been, so I generate, I have a sequence, I called it magic, this one, sequence, okay? So the sequence, this magic sequence is in the computer. What's the algorithm? Take an initial point, get the derivative, and take the step lambda 1 in that magic sequence. In the second point, take the step lambda 2, and go on, and it solves your problem. It may fail for this sequence that I generated if your condition number is over 1 billion. It may fail, but it won't.
So it's conceivable that after a very large number?
No, it's not conceivable. It's that the proof must be done by induction, and it's a mixture of discrete and continuous things there that's very tricky. So I've been working a lot to find an induction hypothesis, but I couldn't yet. But up to 1 billion, it's proved.
One question more there.
Yes?
Concerning your infinite dimensional problem, you make the discretization of the function there, right? I wonder whether you have a convergence result for that discretization, since the function looked very non-smooth.
Look, it doesn't matter what the discretization is. What we do is, when you discretize it, you solve the problem for a function that is an upper bound to the original function. So if you decrease the upper bound, you decrease the function. So you choose the discretization. If you can solve the problem for this discretization, and you have a good solution, then the original problem is better than that, because it's an upper bound. That development, this idea of doing a discretization and finding an upper bound to the functions, took me a long time. It's very simple, but needs about 15 minutes to explain. Well, how many points in the discretization? The number in the discretization that you should use is this number that's expected to be, is square root of c over 2 log of 1 over epsilon. If you use this number of points in the discretization, everything works well. It's not very easy. Yes?
In the large data set problems that people want to solve, what are the size of the condition numbers that you have to deal with?
I have no answer. I believe it's usually up to 1 million or so. I mean, I don't know of problems with condition numbers worse than 1 billion. But then you may have. Yeah. But I don't know what's the use of this, because this is only for quadratic functions. So how do we use these results for general convex functions? I don't know yet. Someone else will find.